Welcome back to Crunch Labs. I'm Mark Rober, and today we're going to be talking about the vacuum chamber and all of the lovely, juicy engineering physics nuggets that go right along with it. Now, if you just got the box and you haven't opened it yet, let me show you what's inside. This right here is a vacuum chamber, and you might be like, well, Mark, that just looks like a cup that sits on this little silicon base here. Big whoop. That's not that interesting. The secret sauce is this little contraption here. And what we've done is basically taken just a normal syringe and then thrown all this stuff around it, so it makes it a lot easier to get a good pump on, which is going to suck the air out of this chamber. If I do this a bunch of times, and now I try and take this lid off, it's really hard to do. We're gonna talk about why that happens in a second. But if I take something like this delicious Peep, it's a little stale because we're like 3 months past Easter. And then I put this adorable little Peep in this chamber, and I do the same thing. Let's observe what happens. He's getting bigger. Okay, so our observation is the Peep got a lot bigger. Now when I allow air to flow back into the chamber by releasing this little plug, it shrinks. What an interesting phenomenon. Why did that happen? Well, today, we're gonna talk about that. So let's get right into it, starting, of course, with the question of the day. And it is, how can you blow up a balloon that's already tied? I've done better. I've done worse. What do I mean by that? Well, here's a balloon that's already tied off, as you can see. How can you blow this up? So you can hand this to someone and say, blow up this balloon, but you can't undo the knot because it's already tied up. Now look, this is kind of an easy question of the day because you've already observed what happened to Peep. You might have an idea of how to do this. Well, let's start with an observation you might have had, because for any good scientist, observation is one of their best tools. That's how pretty much all amazing discoveries come to be, is you notice something and then you're like, why is that? Something you might have noticed is that when you drive up into the mountains or when you go up on a flight sometimes, a bag of chips goes from looking like this to being like fully puffed out. Like you could squeeze it, and instead of being able to dent the bag like this, you could barely push it in. Why is that? Well, let's run a few more experiments in our mini air chamber here, and then we'll come back to this question. There's a very good mental model, a way to think about this, that helps explain everything you're about to see on this table. All right, we already did a delicious Peep. Let's try just a normal marshmallow. Now, watching at home, I want you to make a hypothesis on what you think is about to happen. I'm gonna put our plug back here in the end. Now I'm gonna pump our syringe. Look at that. Just like the Peep, because this is also a marshmallow, it got extra big. And now when I release the pressure, how cool is that? It gets all shriveled and small. All right, let's try something else. We got some bubble wrap here. You know how if you get a package, it comes with this bubble wrap, and it's kind of fun to sit there and pop them. It's very satisfying. Well, you know how I always like to build machines to help me do things easier. What do you think's gonna happen if we put this bubble wrap into our vacuum chamber? If you're thinking what I'm thinking, this might be the lazy engineer's approach to popping bubble wrap. Let's see if it works. Sure enough, it's getting bigger. Pop, pop, pop. They all popped. Now if I release the pressure, oh cool, it went to the top. Look at that. You know how much time I just saved myself? I didn't have to pop all these individually. Science. All right, now I've got some shaving cream here. Let's see what happens when I put this inside. This is actually gel shaving cream. I'm very skeptical this is gonna work, but science is all about experimentation. Here we go. Whoa! That actually is working pretty well. It's getting bigger! So that little bit of shaving cream ended up expanding to fill the whole chamber. Now for the fun part, we release the pressure. Whoa! Just disappeared to nothing. Okay, well now that we've made some observations, let's talk about that and try and understand what's going on. One of my favorite mental models when it comes to understanding the world around us, we've talked about this before, is that air is a fluid. It seems like there's nothing here in front of me, but the space in front of me is filled with air molecules, and they're fluid-like. And by the way, it's not just the space in front of me, it goes all the way up until you get to outer space. Now, I've drawn this here so you could sort of see. Now, all these little dots here, although they look like snow, they're supposed to represent air molecules. And what you'll notice is there's more little dots down here than there are up here as you go higher and higher into the atmosphere. So basically, there's a bunch of air molecules way above us. And it's kind of like if you're on the bottom of a dog pile and there's people on top of you, it's way worse if you're on the bottom than they're on the top, right? Because everyone above you stacks up and you're feeling all that weight. Well, we're kind of being dogpiled by a bunch of air molecules above us. So we're feeling the force of all that weight. And we call that air pressure. It's kind of like if you swim to the bottom of a swimming pool, you can feel it in your ears. As you go deeper and deeper into the pool, you're feeling more of the water molecules on top of you sort of dogpiling. So you're feeling a higher pressure. So here's the question. What happens if you were to remove that pressure? If you were to remove all of the air molecules on top that are kind of pushing down on you? Well, that is what a vacuum chamber is. We create a little tiny space where we suck out all those air molecules, and then you get to see what happens if there weren't any air molecules pushing in all around. So maybe now you can see why, if you take a bag of chips and you take them up into a mountain, well, guess what? The higher you go, the fewer air molecules there are above you pushing down. So as a result, the bag doesn't have as much pushing in on it, and it expands up. And that's actually what I've drawn here. This is the vacuum chamber with air all around, and then you have the chip bag with air inside. Again, that's our little dots. So it's sort of equally crowded with air molecules inside the bag as well as out. But as soon as we pump out all of the air, right, and now there's no dots out here, it's way more crowded in this bag with air molecules than outside. So then it wants to expand. An analogy would be like, in this scenario, it's a bunch of people packed in on a couch. You're all squeezed in, there's nowhere to go. It's equally crowded everywhere on this couch. But as soon as half the people leave one side of the couch, what are you gonna do? Well, you're gonna spread out now and get more comfortable, right? So that's what these air molecules in this bag are trying to do. Suddenly, all the air molecules in here are like, whoa, there's way more room out here on the couch. We want to move into that section. But then the bag itself is sort of retaining and keeping that from happening, which is why it puffs up. And that's the same reason when we put the PEEP in here, you've got all these little air molecules trapped in a marshmallow. That's how they make marshmallows. You kind of whip up the sugar and it gets puffy because you trap all these air molecules. But as soon as I put the chamber on and suck out the air, well, suddenly all those air molecules are like, whoa, there's way more room on the couch. Let's spread out into this chamber, and then that's what causes the PEEP to grow. Here's another fun little experiment. I've got a pot full of water here, and now I'm gonna create a vacuum in our chamber. So again, the model is I'm sucking out all the air molecules. This bottom one, all those little dots are going away. Now if I release the plug here, that's gonna allow air to rush back in. But what happens if I put this underwater? Now remember, all this air pressure out here is dogpiling, pushing down on the surface of the water. What do you think might happen? Let's take a look. Here we go. Wow, so there's a couple really interesting things to point out. The first is you'll see there's still a little air left in here. That's because I didn't get a perfect vacuum. So the amount of air you see at the top of this is the amount that was still stuck in there. There were still a few little dots of air molecules in that bottom one. It wasn't perfectly clear. That's those that are left up there. The other thing you'll notice now is the pressure is equalized, so this cap should come right off, and indeed it does. So the way to think about that is there's all these air molecules pushing down on the surface of the water. So as soon as I open this up, basically it pushed the water through to fill in this space because there was a vacuum in there. There was no air molecules. It was imbalanced. It was an empty couch. So the air pushed down on all this water to kind of more equally fill out the couch so everything was at equilibrium. Let's run a few more experiments. So this right here is a little bit larger. Throw that down. of a vacuum chamber. So this is our version that we manually pump. Now we have an electromechanical pump that when I plug it in and turn it on, it's gonna go and it's basically gonna be like pulling all the air molecules out of this chamber, creating a vacuum inside. Now, if you think about what makes something fly, is you have these propellers, right? And remember, we have the mental model that air is a fluid. So as these rotors spin around, they move around and they crash into air molecules, and it pushes the air molecules down. Well, Newton's third law, if you push against something down, there's an equal and opposite reaction, and that is what pushes the drone up, right? Same way if you stick your hand out the window and you move it like this, you kind of feel your hand move up because all the air molecules are crashing into it. This is like the blade of a propeller. So as these spin, they push against all the air molecules and they go up. Well, what happens then if you put a drone inside a vacuum chamber? Because remember, when we do that, all the air molecules go away. We're creating a vacuum. So what do you think is gonna happen? We actually did this at the lab and you can see what happens here. So basically it flies fine, there's fewer and fewer air molecules, and then it stops flying. And that kind of makes sense, right? Now here's another question. When I turn on the vacuum here, you can see the dial move over. That's indicating that it is at a much lower pressure, basically saying, hey, there's way less air molecules in this little cube than there are out here. And now I try and lift off this lid. It is absolutely impossible. Why is it so impossible for me to lift off this lid? And you notice the same thing with your own vacuum chamber. Super easy to lift it off here. As soon as we pull a vacuum, see there's still some water in there from our other experiment. It's super hard to pull it off. What the heck is going on there? Well, again, there's all this air above us dogpiling on top, pushing in from all around. And now as soon as you don't have air pressure inside there, pushing back out equally, when I'm trying to pull this off, I'm really trying to push up on all of this air, so it's really hard to do. It's like a one-sided tug-of-war, and this side is totally dominating because there's nothing pushing up and out from inside. There's no air pressure inside. As soon as I let air in though, now it's completely easy because the tug-of-war is equal. Now there's more air molecules in, it becomes this situation, and then it comes right out. Another very cool demonstration of this concept of struggling to pull off the lid or struggling to pull off this chamber, the same concept behind suction cups. These are darts from the first dart gun I ever owned. Not very accurate. But basically, at the end of these, you have suction cups. And when you put it down on something smooth, it creates a mini vacuum in there, right? Because when you push down, all the air goes out. And now, all the air dogpiling on top of it is making it hard, so I can't push this up. I'm losing the tug-of-war. And eventually, you can get it out. One of the ways you could lift big, flat, heavy metal plates is using the power of vacuums. So you have something like this. As soon as I push this lever down, it's doing the same thing here. It just created a vacuum in there, and now suddenly, it's super easy to move this heavy metal plate all around, right? What do you think happens if I release the vacuum? The plate drops. And now we'll just talk about one more thing, which has to do with eggs. This egg right here might just look like a normal egg, but this is a world record egg. This is the very egg we took all the way up to space and then dropped it down and it landed safely. Mwah. I just let it sit for a while. This, however, is just a normal egg. Now, if you recall in that video, something we had to do when we sent this to space was to put it in a vacuum chamber to see what would happen. In fact, this is something we could test right here in our own vacuum chamber. So I'm gonna put this up. I'm creating a vacuum. Okay, I'm pumping it up. What happens? Definitely a vacuum. I can't pull this off, but kind of nothing. The egg looks fine. And what does that mean? The egg is strong enough that it can withstand a vacuum, but you don't know until you test it. This is why at NASA, whenever we build hardware and we send it up to space to send it to Mars, any hardware that I built, we had to put it into a vacuum chamber to test it. We'd put it into a vacuum chamber and then we'd get it really cold and we'd get it really hot and we would cycle it and make sure, yeah, this hardware still works even if there aren't a bunch of air molecules around it. It's just a test that you've got to do. In fact, one year for the Super Bowl, I had the opportunity to build a football that would be thrown from the space station to kick off the Super Bowl. They were going to throw it down, and they asked me to design a football that wouldn't pop in space. So I 3D printed this thing. I put this foil inside. You know why I had to put the foil inside? It's because leather is basically invisible to radar. If you didn't have the foil in there, it would kind of seem invisible. So I cut open the football. I put inside this 3D printed thing to sort of give the skeletal structure so it would still seem like a football, but wouldn't have all that air in there that would be pushing out and potentially pop the football. We had it all ready to go, and then at the last minute, NASA pulled it off, and they didn't allow us to send it to space, dang it. But that would have been cool. But it's just an example of something that you have to think about when you're designing hardware to go to space, just like our egg that went to space, to make sure, hey, will this crack? Will it not? And it's just something as an engineer, you've got to be thinking out and you've got to test. So the secret to making this work is you have two one-way valves at the bottom here. So as you move the syringe up like this, it allows air only to come in through this valve. And then when you move the syringe back down, it allows air only to pass out this valve. And you could double check that's what's happening by placing a balloon on the outlet valve. And if you put a second balloon on the inlet valve, you can see it immediately creates a vacuum. And it's that same ability to suck all the air out from this side and then to push it over here that we use to create that vacuum inside our vacuum chamber. I've saved perhaps the best demo for last because I've got a little bit of warm water in this beaker. The warmer the water, the easier it'll work. I'll explain that in a second, but I put it in our vacuum chamber, and then when I pump it up, I've also put a balloon here because it's just a fun way to show that the air is indeed being sucked up here in the one-way valve and then passed out here through the one-way valve. So as I pump this, first of all, you'll see that balloon filling up on the outlet one-way valve. And if you watch carefully on our little beaker of water, as I lower the pressure, bubbles start appearing and it boils. We're making boiling water. How cool is that? We're boiling water, literally, that's close to room temperature. By the way, another pro tip on these pumps, you'll get the best pressure right here at the top. So you really want to fully extend it. Instead of doing little ones like this, really let the syringe come all the way to the top before you push back down. Now what's going on there? Well, if you've ever been camping, again, going into the mountains, you might find that it takes longer to cook stuff when you're boiling it. And that's because things boil at a lower temperature. In the same way we got this water to boil that was almost at room temperature, it would take much longer to hard boil an egg in the mountains. Basically, with less air pressure pushing down on the top of the water, it allows the molecules to go into a different state and to evaporate a lot easier. This is also the trick if you go the other way to pressure cookers. So a pressure cooker makes the air pressure a lot higher and then the boiling point goes way up, which means your food could cook at a higher temperature, which is why it happens faster. So a pressure cooker is like the opposite of trying to cook something in the mountains, and it all has to do with air pressure and vacuums. All right, well now it's time to answer our question of the day. How can you blow up a balloon that is already tied? You guys should definitely know the answer to this. I've got this tied balloon in here. If I stick it inside our chamber, then I pump it up, what's gonna happen? Well, this makes sense. It's just like the bag of chips, right? It's trying to spread out on the couch because there's no more air molecules in our vacuum chamber. And you blow up this balloon magically without undoing the knot. All right, so now we'll cover how to put it together. As usual, you know the drill. You can use the paper instructions, or you can follow along video and just pause, or some combination of both. As usual, it'll take me about 4 minutes to do on video. It'll just take you anywhere from 20 minutes to an hour to do it at home. First, grab the yellow adhesive foam and one of the matching wood side pieces. Peel one of the paper backings off the yellow foam and stick it to the wood side piece. Next, find the large plastic syringe and remove the plunger from the syringe and place the handle of the plunger into the corresponding T-slot in the wood side piece. Locate both dark blue wood pieces and slide the dark blue wood pieces into the two slits in the wood side piece. Now locate the second wood side piece that matches the yellow adhesive foam and peel off the remaining paper backing from the yellow adhesive foam and stick the second wood side piece over it. Now both blue wood pieces and the plunger are locked in place. Next, find one of the large wood handles and one of the small yellow spacers, and drop the yellow spacer into the small hole at the top of the handle. Now slide the top end of the handle in between the dark blue wood pieces until the hole in the yellow spacer lines up with the holes in the wood pieces. Now find one white bolt and one white nut, and slide a bolt through the aligned holes and use a nut to lock everything in place. Now grab the remaining large wooden handle along with a yellow spacer, a nut, and a bolt. Repeat steps 6 and 7 by inserting the yellow spacer into the top of the handle. Then slide it in between the dark blue wood pieces and screw it all together with a bolt and a nut. Now gather the plastic syringe body, the wooden circle, and the blue plastic collar piece. Slide the syringe into the blue plastic collar and place the wooden circle on top so that the holes in the wood circle line up with the holes in the plastic collar. Next, find the 4 white bolts and 4 white nuts. Use all 4 white bolts and nuts to attach the wood circle to the plastic collar. These 2 pieces will sandwich the syringe body into place. Then grab 1 red wood piece, 1 yellow spacer, and 1 white bolt. Place the yellow spacer into one of the holes in the blue plastic collar, then slide the bolt through the red wood piece and the yellow spacer. Now find another red wood piece and a white nut. From the other side of the blue plastic collar, slide the second red wood piece onto the bolt and lock it in place with the plastic nut. Then grab 2 more red wood pieces, 1 more yellow spacer, 1 more white bolt, and 1 more white nut. Repeat steps 11 and 12 by placing the yellow spacer into the remaining hole in the blue plastic collar. Then slide the bolt through the red wood piece and the yellow spacer. Then from the other side of the blue plastic collar, slide the second red wood piece onto the bolt and lock it in place with the plastic nut. Now grab the plunger assembly and slide it into the syringe assembly. Now find 1 yellow spacer, 1 white bolt, and 1 white nut. Drop the yellow spacer into the remaining hole in the wood handle piece. Then slide the handle piece in between 2 of the red wood pieces until the hole in the yellow spacer lines up with the holes in the wood pieces. Then slide a bolt through the aligned holes and use a nut to lock everything in place. Find another yellow spacer, white bolt, and white nut, and then repeat step 15 for the other handle piece. Drop the yellow spacer into the hole in the handle, then slide the handle piece in between 2 of the red wood pieces and bolt it in place. Now it's time to test your pump. The linkage you just built is called a scissor linkage. It's designed to give you a mechanical advantage when pumping the syringe. And mechanical advantage is basically a real-life superpower because it multiplies the force that your muscles can produce on their own. Next, find 3 short sections of clear tubing and the clear plastic Y fitting. Slide a short section of tube over each of the 3 ends of the Y fitting. Now grab 2 one-way valves and insert each one-way valve into the 2 bottom tubes on the Y fitting. One-way valves allow fluid to pass through in one direction but not the other. You can discover the direction of flow by looking at the valve's body, which is shaped like an arrow. So make sure the left valve has its arrow facing down and the right valve has its arrow facing up. Grab one of the long sections of clear tubing and slide it over the right side of the one-way valve. Remember that this should be the valve that has the arrow facing up. Find the blue plastic base and another long section of clear tubing. Slide both long sections of clear tubing over the 2 nozzles on the bottom of the blue plastic base. Now find the red plastic cork and plug that cork into the long section of tubing coming out of the blue plastic base. Make sure the ribs on the cork go all the way into the tube to create an airtight seal. Now grab a rubber band and from the bottom of the blue plastic base, stretch the rubber band up over the lip. Find the white rubber gasket and the clear plastic dome. Place the gasket on top of the blue plastic base, then place the clear dome on top of the gasket. A gasket, by the way, is a soft material that creates a seal between 2 objects. Without a gasket, your vacuum chamber wouldn't be airtight. Finally, plug the end of your syringe into the Y valve and you are ready to go. All right, well for the engineering hustle today, I really like this as a brain teaser. You could just walk up to someone and be like, how can you blow this up without undoing the knot? And see them try and think of all different ways, and when they give up, you pull out your vacuum chamber and you blow their mind. Well, great job today. As usual, engineering is an iterative process. I think this build, more than most, is very conducive to just going out and experimenting and trying different things to put in your chamber. One thing we didn't do today that I thought would have been fun is to use the white shaving cream because it's a little more foamy. Maybe put some drops of food coloring in there and then do a vacuum and see what happens. You might find some things don't react at all to a vacuum chamber, like an egg, because the shell is just strong enough and there's not a lot of air molecules inside the egg, so just nothing happens. Then try and figure out like what types of things do react in a vacuum chamber, what types of things don't. Try and figure out what the difference is and why it matters. Why does, say, a penny not do anything, but shaving cream does? Test a bunch of stuff and figure out what the difference is, especially now that you kind of have some of the principles down and the mental models of what's actually happening there. Either way, no matter what you do, make sure you work with your parents to post it on our socials at Crunch Labs, because I love seeing all the clever ideas you guys come up with and all the different ways you could take these builds to the next level like a true engineer. All right, so that's it. You have earned your gear badge for vacuums, so go put this thing together, have some fun experimenting and learning, and then I'll catch you next month right here back at Crunch Labs.